Okay, hello everyone. This video is about the validity of this formula. Angular momentum about a point P that can be given as the inertia about the axis of rotation times the angular velocity, which is of course directed along the axis of rotation. So is this formula always correct? So this is always correct whenever the object is planar and the axis of rotation is perpendicular to the plane. So in that case, you can always do this thing. So why does this formula even work in the first place? You might think that maybe that's the way angular momentum is defined. Well, no, angular momentum is defined by this summation. It's a summation of mi ri vector cross vi vector. So that's the way angular momentum is defined. And now for this particular case, you can always write vi vector as omega vector cross ri vector. So this can be written as mi vector, sorry, mi, and then you got ri squared and then omega vector minus ri vector dot omega vector times ri vector. So in most cases, so the most cases that you will see in, let's just say, the usual physics that you might come across, right? So in those cases, this axis of rotation will be perpendicular to the plane. So then you can just say that ri squared, that's also just r perpendicular squared, where r perpendicular is the perpendicular distance of a point from the axis of rotation, right? And of course this dot product will just be 0 because omega vector is perpendicular to ri, and then that's why you can write this as summation of mi ri squared and that times omega vector, and that's how I times omega vector works. But now the question is, what happens if this term is not 0, and what happens if ri vector, sorry, ri squared, right, if that thing is not actually r perpendicular squared? In those cases you can actually not apply this formula, and instead you have to first of all check if this formula is, somehow applicable or not, right? That is, if you can figure out angular momentum in some other way and see if actually it matches with this formula. So right, the first case that we'll go for when this doesn't seem to be working, that is this thing. Let me just show you what I mean. So you got a ring and the axis of rotation is passing through its diameter, right? Yeah, and we'll just say, okay, this is the x-axis, this is the y-axis, and we need to figure out if the angular momentum, and it's of course rotating by angular velocity omega about the y-axis, and this is the origin, of course, so the origin O. So we want, and by the basis of uniform mass density, right? Now what we want to find is the angular momentum of this whole ring about the origin, right? And we want to verify whether or not this angular momentum can be given as the inertia about this axis times the angular velocity, that is of course omega j hat. So the inertia about this axis using the perpendicular axis theorem, it's going to be mr squared upon 2, where m is the mass of this whole ring, r is the radius, and then that thing squared, and then upon 2, right? So angular momentum would basically be mr squared upon 2 times omega j hat. That is what we expect, but is this correct or not from the fundamental principles? So as always, our angular momentum is given by summation of mi ri vector cross, now vi vector can be written as omega vector cross ri vector, right? But then you see that ri vector can be broken down as an x component, as a y component, right? So because angular velocity is completely in the y direction, so the y component crossed with the angular velocity, that's going to give us 0. So this whole thing can actually just be written as omega vector cross rx vector. So basically omega times x, where x is of course this coordinate, I should say xi because we are still in the summation, and then this was basically like j cross I, and that's why it's supposed to be negative k, I think. So negative of this thing times k hat, and then you want ri vector cross this whole thing, and then ri vector can be written as x I hat plus yj hat. So let's do the cross product, right? So xi hat cross this whole thing. So remember, I cross k, that's going to be negative j hat. So this just turns out to be omega xi square, and in j hat, of course. But the other thing, so y j hat cross this whole stuff. So j hat cross k hat, that would be just I hat, right? So you're gonna have I hat over here. This negative still is there, and then you got omega xi yi, right? Okay, so it looks like this term is all that should remain. That is, this should get cancelled so that we can actually get this value, because as you can see, xi squared is, and then that times of mi, that's the inertia of this small particle from this about this axis, right? Yes. So this thing is actually, I mean, okay, this summed, right? So this part is actually going to give us I omega j hat. But what about this part? So the other part is just negative summation of mi omega xi yi I hat, right? So is that part 0 or what, right? So to do that, let's use a parametric form. So we'll say that this thing is given by r cosine theta comma r sine theta, where theta is this angle, right? Okay, and then this whole summation can be thought of as this integration. So integration of dm, and by the way, I'm excluding this omega and I hat from here. I'm just trying to prove that this is actually 0. So I will just keep it short, I mean as short as I can keep, and exclude all the unnecessary constants. So you're gonna have dm instead of this thing. This summation becomes an integral. Then you just got x and y. So x and y, that's going to be like r squared cosine theta sine theta, right? And then dm is basically rd theta. It's like this integration of r cubed cosine theta sine theta, and then you got d theta. So you can take this r cube out, and then that's just an unnecessary constant. We don't even need to look at that. And you know what, let's do this thing, 2 over here upon 2, actually upon 2 once again, so that you can put 2 over here as well. So then it's just integration of sine 2 theta d2 theta, that's what we look for, of course. And then 2 theta is going from 0 to 4 pi, right? And this unnecessary stuff, we just skip the whole thing. So I mean, it's going to be 0 in any case, right? That's what I'm trying to prove. So this is going to be equal to negative cosine of 2 theta going from 0 to 4 pi. So 2 theta is actually going from 0 to 4 pi, huh? Remember that. So yeah, instead of 2 theta, you could just use something else like phi or whatever you want. So it's negative cosine of phi going from 0 to 4 pi, and this just turns out to be 0. Now some other cases as well give us 0. That is, if you just got this semicircular arc or just this semicircular arc, in those cases as well you will just get 0. Because you will just have, you know, cosine of phi going from, so if you got this kind of arc, theta is going from negative pi upon 2 to pi upon 2, but then phi should go from negative pi to pi, and then this still turns out to be 0. If you got this arc, then theta is going from 0 to pi, so then this thing must be going from, so phi must be going from 0 to 2 pi, and then this still turns out to be 0. So in these cases, yes, L equal to I omega actually works out, but that's just a coincidence. We don't know for sure whether or not it's actually going to work out all of the time. So yeah, that's all I wanted to say, right? So just be careful while using this formula. It might or might not be correct. And just on a side note, why did I even think about this whole thing? So what I was trying to do is, you know, you got this disk, and you got angular velocity vector going like this. So this is the axis of rotation. It's a uniform disk, and you just want to figure out what's the angular momentum about this point, right? So to do that, what we can do is split this angular velocity into 2 components, so like this and like that. About this component, finding the angular momentum is very easy, but for this component it's going to be very hard. And by the way, you can actually split the angular momentum into basically the sum of, you know, angular momentum about this axis of rotation and about this axis of rotation, right? So why can we do that? So you just got summation of mi, and then you got ri vector cross, so maybe I should just not put in a bracket, okay, cross. So the total omega vector, which I will say is like omega 1 vector plus omega 2 vector, and then this crossed with Ri vector once again. So because of distributive properties of the cross product, you can actually split this apart over here. So you can write it as omega 1 vector cross Ri vector plus omega 2 vector cross Ri vector, but then you want to apply Ri vector on this thing, so you can once again split this, and then of course this times mi. So you just want to sum these two quantities in fact, right? And this is basically the angular momentum, right? This whole thing is the angular momentum about omega 1, right? Which is easy to find. So it's just going to be equal to the inertia about this axis times the angular velocity, the unit, the vector of course, not just the value. And then this thing is harder to do, so it's about this axis of rotation. Yeah, and that's a tough thing to do. So that's it. So I'll see you guys in the next video. Bye.